session. I apologize for the cancellation of the first talk. Now it is 4:30 Buenos Aires time, and we continue our program with a talk by Ariel Pacceti from the Universidad de Córdoba, and he will tell us about Heike characters and some Diophantine equations. Please, Ariel, go ahead.
Okay, so I want to start thanking the organizer for inviting me to give this talk. So most of the things I'm going to talk about are in a joint work with Lucas Villagra Torcomian, who is a student of mine. So I'm going to give a talk which is more like a panoramic idea of how you use this modular method to solve some equations, but I'm going to focus in this particular case. So the question is the following: suppose you start with this is a sort of Fermat type equation, but know that the exponents are a little different. So the exponents are like 2,6p instead of ppp. So in particular, the solutions belong to a surface instead of a projective curve. So sometimes this is a different situation. For example, we don't have Folting's theorem here, which says that you expect finitely many points. And so you might wonder what are the solutions of these sort of equations, and this is somehow what we want to do. So I want to mention that while I was sending the abstract late, I think it was 1 hour before the deadline or something like this. So when I posed the question, I just posed how many integral points, and I forgot one of the big hypotheses, which you want to impose some conditions. So I got an email the next day from Andrew saying, of course, you have infinitely many of them. And then he sent me this nice source of points, which I knew they usually exist, but I didn't have an explicit formula for them. So the answer, if you don't impose any condition, then is there are too many of them. This is just the formula for primes congruent to 1 mod 6. He also sent me another formula for the other ones, the congruent to 5 mod 6. So I want to rephrase and post the right notion of what do we want. So P is going to vary, and D is going to vary as well. And so the good notion is what are the primitive solutions? So what is a primitive solution? A primitive solution is a solution where the 3 coordinates of the solution are prime to each other. So you don't have any non-trivial factor. Note that in general for the Fermat equation, since it's a projective equation, you can always restrict to primitive solutions because you can just get out the GCD. But this is not the curve, this is a surface. So you cannot do this procedure in this context. But know that this is a very interesting situation because you have infinitely many non-primitive solutions, but what we expect is to have actually finitely many primitive solutions. And also in the same email, Andrew sent me a proof assuming the ABC conjecture, which is more or less standard, but still he filled in all the details of why there should be finitely many, but we will use a completely different method. Okay, so let me just give the general strategy of how do we usually try to handle this sort of solutions. So the strategy, which is mostly due to Frey, but there were some ideas before that, is you try to attach, you assume you have a solution, a non-trivial solution, and then you try to attach some geometric object to your solution. In general, this object will be an elliptic curve, but sometimes it's not so easy, but everything I'm going to say will be an elliptic curve. And once you have this geometric object, then somehow the idea is you try to understand what are the properties of this geometric object. So for example, what I mean with properties, if you have an elliptic curve, it's given by an equation. I'm going to go to this in the next slide. And then you can try to study some of its invariants. For example, the discriminant, where do you get bad reduction? What are the image of the Galois representations? So you have a lot of information attached to this geometric object that you have to try to understand. In particular, you like to prove that this geometric object is attached to some analytic object, and these are in general modular forms. So in the case of Fermat-Last theorem, then you do get genuine modular forms. In this case, we're going to have to go a little farther. And then once you know that you have an analytic object attached to the geometric, to the putative solution of your equation, then what you do is you just go and try to compute some particular space of forms. So I'm going to go to this in a minute, it's a miracle that you can get something which does not depend on the solution. You just get one concrete space of forms where you try to search for a form attached to a solution. So this is step 3. You have to compute some space of modular forms. You do just by any computer program like Sage, Magma, or the one you prefer. And then you try to actually prove that none of the forms in this space is related to a solution of the original equation. So this is more or less what is somehow the standard modular method that is used in many different instances. So let me go back a little bit to each one of these in the particular problem that I discussed before, which is this equation, which was x squared plus dy to the 6 equals c to the p. So step 1 says that you have to come up with some geometric object attached to it. So in this case, what we do is we attach to a putative solution. So A, B, and C are going to be the solutions. So A, B, and C are the pairs coming from a solution attached to our equation, and we're going to construct an elliptic curve out of it. So the elliptic curve is the one given in this yellow mark. It's y squared plus 6b square root of minus d times xy minus 4d a plus b cubed square root of minus d times y equals to x cubed. Then you may wonder, how do you come with such an equation? So the idea when you try to search for this equation, there is not a way to get an equation. And actually, there are many different geometric objects attached to a solution. Oops, my computer got disconnected. But so okay, my computer got disconnected. I don't know why. Okay, so let me, sorry for that. I don't know why you can still see that. Okay, so what you can try to do is the following. Maybe I can share. These are the sort of things that are not supposed to happen. Sorry. So let me share my computer. Okay, so can you see the computer? Okay, I'm not going to be able to write on it, but at least can you see it?
Yes, we can see it. We can see it.
Sorry for that. So the idea is the following. You look at this. So the idea is, what are the important facts here? The important facts here are, first of all, the discriminant. Okay, so if you look at the first property I wrote there, it's the discriminant of the elliptic curve. So when you have your equation, which was x squared plus d times y to the 6 equals c to the p, you can factor the left-hand side over this quadratic field, and this is where the quadratic field appears, and you can just write it as a difference of squares, and that this is where this a plus b squared b cubed square root of minus d comes from. And so the idea is that since you know that these are a power of p, because you have on the other side of your equation c to the p, then let me see, it's appeared to have p. Okay, there you go. So then the advantage, since you have c to the p to the other side, you know that this part here, all this part is a pth power. You see, and so the advantages of this part being a p power is that you're going to be able to somehow to get rid of this by some standard method, which is called this lowering the level, which is a result due to rivet. And so somehow you will end up with a number which doesn't depend at all on your equation. You see, the part that will remain is going to be this 2 to the 8 times 3 cubed times d to the 4th. And this is the space of modular forms that you're going to try to compute. So, but note that this elliptic curve is a weird elliptic curve because it's not defined over Q, it's defined over a quadratic extension. So, and it's even if this is positive, it's an imaginary quadratic extension. So we don't have modularity of these elliptic curves. So in particular, you need to attach an analytic object to this sort of equations. But the property that this elliptic curve has is that if you look at its Galois conjugate, Okay, it's related to the original curve, which is this third condition that I wrote here. So if you, the curve has a particular point, which is 0, 0. It has order 3. So if you add the point 3 times, you get the 0 in the curve. And if you mod out by this point, you get the conjugate curve twisted by the quadratic character attached to the extension q of square root of -3. And this means that your curve is a q curve. So what does it mean to be a q curve? So a q curve is an elliptic curve which is defined over any number field. It doesn't have to be defined over q, but with the property that when you look at its Galois conjugate, so you just take your equation and you apply any Galois conjugation, so you get another equation, and you want all these curves to be isogynous to each other. So what's the good point of having q curves? So this is a result of Rivet, which says that if you have a q curve, then somehow the representation you get after twisting, you can extend it to a Galois representation over the rationals, you see? So in general, when you have an elliptic curve over a number field, you can attach a representation, but over the field of definition of your curve. And so the advantage here, when you have a q curve, is that actually this representation, in our case, which was defined over q squared of -d, we can extend it to a representation of the whole Galois group of q bar over q, and still get a two-dimensional representation. So the Rivet's proof goes as follows. So to a q curve, you can attach some cocycle, some cohomological cocycle, and then it's a result of Tate that this cohomology group, if you extend scalars, then it's trivial. So it means that somehow what you have to do is you have to trivialize a cocycle. Okay, and how you trivialize this cocycle will be related to the twist you have to start with. Not that we want to find a particular space of modular forms to compute with. So somehow what we need to do is we need to find this twist explicitly. So instead of trying to trivialize this cocycle, which looks a little like a hard thing to do, we should do something a little different, which is the following. So remember that what I say is that our elliptic curve, if you look at the Galois conjugate of your curve, it was isogynous to a twist of the curve. So isogynous means that the Galois representations are exactly the same. So I'm going to take a generator for the Galois group of the quadratic extension, and I start with the Galois representation attached to my elliptic curve, and I consider another Galois representation, which is this tau, this rho e tau, which just what you do is you just take any element and you conjugate by this tau. This is again an element of your Galois group of the quadratic field, and you evaluate your representation there. So this is the representation attached to the conjugate elliptic curve. And the condition on that the conjugate elliptic curve is isogynous to a twist of the original representation implies that you get a particular relation between these two Galois representations. Okay. So how do you find the character? Remember that we're searching for a character. Okay, so this the first part is I just copy the last part of the previous talk. So the idea is to try to find a Hecke character which satisfies exactly the same condition. Why is that? Because we want to twist the representation. Then if we multiply the two left-hand sides of the equality, it will going to be the same as if we multiply the two right-hand sides, and then this quadratic character cancels out. So if we find a Hecke character satisfying the pink relation, then this is the right twist we're searching for. But note that this condition that I wrote over here, this goal, now it's something that has nothing to do with any elliptic curve or the Fantine problem or nothing. So I'm just searching, I have a quadratic field and I'm searching for a Hecke character satisfying a particular relation. Okay, so this is now this is a completely different problem. How do we construct Hecke characters? So remember that the Hecke character is a character of the ideal group of your field to the complex number. I want it to be finite, so it will be not so hard to construct, but still Hecke characters are very tricky. So how do we construct such a Hecke character? So the idea is the following. We want to construct a Hecke character whose value is going to live in the ideals of K. So we want to construct something here in the middle part. Because it's a Hecke character, it's trivial in K star. So the first part, the K star part, it's easy, it's trivial there. Okay. Now the second part, it has to do with the units. Okay, this OP star, if you think about the integers, it's just defining a character of a CP star. And this is Dedekind's characters. Okay, you just have to say which power of P you need to take, and then you have to define it in a generator, because these are all, except for P equals to 2, all the other ones are cyclic groups. Okay, so the idea is we're going to construct the Hecke character at units, satisfying precisely the same condition I want the whole Hecke character to satisfy. And in this way, I'm going to construct the Hecke character in the left-hand side. The hard part is to define it in the class group, okay? Because I mean, it's a general quadratic field, so I don't have any information on the class group. So how do you define it on the class group? And so remember that I started with the representation rho, and I'm going to try to twist it by a character, this character he, okay? And so after I twist, I want to extend this representation to Q. So the determinant of the representation is going to be the determinant of this twisted representation, which is this character square. Okay, so what I'm going to try to do, first of all, is to construct the Neven-typos that I'm going to end up with. So the determinant of the representation upstairs is going to be he square, because when you twist by a character, the determinant gets square. And so I'm going to search for a character downstairs which somehow extends the square of he. And if I can do that, then I can extend my character to this class group just by defining epsilon in the norm of an ideal and then taking the square root. So this is somehow the way we construct. There are many things you have to check. And there are two big and important subtleties here that I just want to mention. So one of them is I define it in the first term of my exact sequence, but note that there is some intersection. So these two sets are not disjoint. So there are some elements which are elements of your base field and are also units everywhere. So what are these elements? Well, they are the units in your quadratic field. Okay. Now I didn't put any hypotheses on D. D might be positive or it might be negative. So when D is negative, your quadratic field is quadratic real. And then this is an extremely hard problem, because then you have fundamental units around going on, appearing in your problem. And so if you want to prove that your character is well defined, you have to prove that the character you just defined on units, it's trivial on a fundamental unit that we don't know how to construct somehow. Okay, so you have always have to prove that it's trivial at -1. So this comes somehow by quadratic reciprocity. But also, when your field is real quadratic, it's harder because you have to prove it's trivial in a fundamental unit. And somehow the issue, the problem there is related to the following question, which I posed to many people, and everyone said, well, the answer should be whatever. And I said, yes, I do agree, and experimentally this is what happens, but I still don't know how to prove it. We actually managed to do it, which is the following. Say you take a real quadratic field K, and you have your fundamental unit, and then you can consider the quadratic extension given by taking the square root of the fundamental unit. And sometimes, if you're lucky enough, this is going to give you a quadratic extension which is unramified everywhere. So you might want to describe it in terms of, remember that K was Q square root of D, say D is positive, and then you'd like to describe it as taking square root of something which has nothing to do with your fundamental unit, something which is related to D. And this is a really interesting problem, but I'm not going to talk too much about it. I can mention the details if someone is interested. But so this is the hard part, try to prove that it's well defined in these units. And once you know it's well defined on units, then you define it on generators of the class group. As I said before, you just take the norm, you evaluate your epsilon, which is going to be your Neven-typos, and then you take a square root. Okay, and so this gives you a well-defined character, and you have complete control on the conductor of the character. This is the key point here. So if you have complete control, then what you can prove is that you can extend your representation to a representation downstairs. Okay, so this is one of the first results. So your original representation, you can twist by this character and get a representation which is a rational representation. Hence, by Sel's conjecture, we know it's modular, so it's attached to a modular form whose level has some power of 2, some power of 3. The power of 2 and the power of 3 has to do with how the prime 2 and the prime 3 behaves in your quadratic extension. We have explicit formula and description for this. then all the primes that ramified in your quadratic extension are going to appear in the level. And then you have some extra primes, which has to do with the primes dividing the value of C, which appear to a pth power in the discriminant. So what do you do here? You may say, well, but I mean, which space do I have to compute? I mean, this n, I don't have any information on them because C is just any solution. And so here's where Rivet's theorem comes in hand, and it says if you're lucky enough, your representation has large image, so I'm not going to say too much about it, then actually all primes dividing n, you can just get rid of them. So you can end up with a concrete space of modular forms, which does not depend at all in anything, but just the quadratic field you started with and how 2 and 3 behaves on it, okay? And so you end up computing forms in this particular space of modular forms. So then you compute this space and you have a lot of modular forms and say, okay, so what do I do now with them? So you choose a basis of eigenforms. And then here it comes the harder part. So how do you discard these forms and prove that they are not related to solutions at all? So the first idea, which is called Mazur's trick, is the following. So you know how to compute solutions mod P because they are finitely many. So take your favorite prime L, which does not divide D, of course, and just compute mod L all the solutions of your equation. So find the finite set of solutions of your original equation. And do the same construction of the elliptic curve for each one of these values of A and B. Now, this is an elliptic curve which is only well-defined modulo L somehow, okay? So it's not well-defined modulo, it's well-defined modulo a prime in the quadratic extension divided L, okay? Remember that the elliptic curve has some square root of minus D. And then if your elliptic curve has good reduction, okay, then what we got from Rivet's theorem is that we have a congruence between the modular forms downstairs, which is this Fourier coefficient of Fi, and the twist of the value of the AP of the elliptic curve. So this is exactly what we did. We started with the curve, we twist, and then we found a form which should match it. Okay, and this AL, you just have to know how to change coefficients from Q to the quadratic field, but it's not important. And if the curve has bad reduction, well, then you're in some case of the lowering the level, which Rivet tells you what are the precise conditions. So what is the idea here? The idea here is if you can compute this, you compute this left-hand side, so there are finitely many values of A tilde and B tilde. And then you take the difference with the AL of your form, and if it's non-zero, then you know that the only primes that might be related to a solution have to be the ones dividing this difference. And so in this way, you get finitely many possibilities for the values of P. And then for all the other ones, you know that the form cannot be related to any solution. So you can just throw it away for all the other primes, okay? So in general, this works, but it allows you to eliminate most of the solutions. But there are some solutions that they always remain. So they're like a pain, you know, what can I do with this? And it's even harder because you always have some solutions coming from the trivial solution, like 101. And when D is negative, you even have more solutions which might come from the equation where C is equals to 1. So x squared minus D y to the 6 equals to 1. So these are really hard to discard in general. And so here's a really nice result of Ellenberg, which tells you that, well, if your solution has the property that the value of C is divisible by some prime larger than 3, then you're in really good shape, and the image of your Euler representation, it's huge. It has to be really, really large. And so in using this result, you can actually get rid of all the modular forms that are the hardest ones, which are the ones which are related to modular forms with complex multiplication. And for example, this includes the trivial solution 101. So if you happen to have a nice prime, then using Ellenberg's result, you can just get rid of all the modular forms with complex multiplication. And if you're lucky enough, then you got rid of everything you could. So let me give you an example. So this is an ongoing project with Franco Gualfieri and Lucas Villaga. So let's take d equals to 11. Okay, now it's explicitly x squared plus 11 y to the 6 equals t to the p. Okay, and in this case, you do the computation I mentioned before. You can know exactly what's the character he was epsilon. So epsilon is trivial. So you have forms with trivial event types. And then you just go to the formula and you say how to compute two spaces. The levels are 2 squared times 3 squared times 11 squared, and 2 squares times 3 cubed times 11 squared. So these numbers are large. I mean, the last one is like 13,000 or something like this. So it takes some time in the computer to compute these spaces. But that's okay. You start with the second one. You just compute the new forms. There are 43 new forms. 11 have complex multiplication. So if you're lucky enough, you're going to get rid of them with LMX result. And you can use Mason's trick and discard all other forms for primes larger than 13. So you just got rid of this second space, you know? So you prove that there cannot be any solution related to any form in this space. Now, if you go to the first space, and you have to be a little tricky here, so since I don't have too much time, you have to prove that you cannot have a situation which is only a power of 3. This is a hard problem that internet, you have to use some S units or something like this to prove that there are no solutions there. But for P larger than 17, this doesn't happen. Okay, now you say what happens with the second space? Okay, I mean, I just said you can discard forms in the first space. So if you try to compute forms for the second space, then the situation is the following. You have 26 new forms, 6 have complex multiplication, so you can just get rid of them. And Mason's tricks works for all of them, but there are 2 remaining ones. Okay, and when you have some remaining form, you cannot prove anything. So it's like, it's not that you got at least a partial result. You cannot say anything at all. Now, if you compute the other spaces, one of the form is a quadratic twist of a form of level 2 squared times 11 squared. And this implies that at the prime 3, the reduction, this form is a twist of something which is good. But the original curve does not have this property. So this means that you can also throw it away. And this is what I talked when I said that you go also to the type of the representation. So sometimes this type, it gives you this sort of information. But you still have one extra form, which has coefficients. The coefficient field is quadratic. But over this imaginary quadratic field, where q squared of minus 11, it corresponds to a real elliptic curve. So let me just mention a problem here. How do you compute the elliptic curve? So this case has a really nice answer. This particular case, it's due to an idea of John Cremona, but doesn't matter. Here here you have an equation for the curve. Okay, and so how do we prove that this curve is not related to any solution whatsoever? I mean, there's still one curve, and if I don't get rid of this curve, I won't be able to prove anything at all. And so still you have another extra information which you can use sometimes, which is that these 2 curves are actually elliptic curves. And it's not just that they have Galois representations, but they have some geometric object behind attached to them. And in this case, what they do have is a veil pairing. And so you can try to understand when these 2 curves might have an isomorphism which is compatible with the veil pairing. And actually what we managed to prove here you have to do something which is the symplectic method. So we use it over ramified extension. So this is something that I didn't see it used before. Maybe I'm wrong. Mike probably knows more than me about it. And you can prove that if your prime is congruent to 3 mod 4, then these 2 curves cannot be isomorphic. So what we can end up proving for this particular equation is that it has no primitive solution if P is larger than 17, and either one of the 2 solutions is divisible by 3, because you have 2 different sort of solutions. The ones which with one of the entries divisible by 3, they cannot correspond to this particular curve. It has the wrong type of reduction at 3, so you know that none of these have any solution, or in general, only for primes which are congruent to 3 mod 4. So it's like you proved a result, but only for half of the primes. Okay, and actually we do expect none of them to have solutions, but this is as far as we can go. So thank you for your attention, and sorry for the problem with the computer.